Okay, so now we want to use Fourier transforms to solve this diffusion equation. And there's nothing really that we're going to do here other than just take Fourier transforms. So I'm just going to begin by taking Fourier transforms of both sides of the equation. When you do that, you get the t derivative of u hat is equal to minus alpha c squared times u hat. Look, this is just a first order differential equation for u in the t variable. And what you get, the solution then, is going to be u hat of ct is going to be equal to u hat c0 e to the minus alpha c squared t. Okay, so what is this? Well, this is just equal, this is just a Fourier transform. So now we're thinking about c as being the variable. So this is going to be the integral u hat c0 like this. Sorry, x goes there. But this, sorry, I got this all sorts of backwards. That's supposed to be like that. This is just equal to g of x. And this is just the Fourier transform of g. So the conclusion is that u hat of ct is equal to g hat of x. Whoops. Wow, what does the matter with me? G hat of c e to the minus alpha c squared t. Okay, so now I want to find the inverse Fourier transform. And using so I'm going to have to use the Fourier transform table in the book, at least in principle. Eventually, hopefully, you'll have most of these kind of memorized just by use, but I'm using this. And there's two things that we're going to use. One is going to be that the Fourier transform of e to the minus a x squared, the Fourier transform of this is square root of pi over square root of a e to the minus c squared over 4a. And two, we're going to use the fact that the Fourier transform of g convolved with f is equal to the product of the Fourier transforms. Okay, so what we're going to do, this one is clearly going to kind of match up with that, and then we want to make this match up with that. Okay, so in other words, I need to find, if that's my f hat of c, I want to use my first identity to find f of x. Okay, so the first thing is I need to make it look a little more like this. So to do that, I'm going to start with e to the minus alpha. Well, I'm going to rewrite it a little bit as e. I'm going to rewrite it a lot, but I'm going to start by writing it as e c squared alpha t. And I need to write this to make it look like this. I need to write it as c squared over something. So this is going to be e to the minus c squared divided by 4 over 4 alpha t. And again, the reason I'm doing a 4 is because there's a 4 there. Or I could write this, so now I see that a is going to be 1 over 4 alpha t. I need to have a square root of pi over square root of a. I don't have that, so I'm going to multiply by the square root of a over the square root of pi. Then I can divide by the square root of a over the square root of pi times e to the minus c squared over 4 alpha t. Okay, the square root of a is 1 over the square root of 4 alpha t, so this is 1 over the square root of pi 4 alpha t. And then this whole thing right there, that whole thing is the Fourier transform. So now a is equal to, a is equal to 1 over 4 alpha t. So this is the Fourier transform of e to the minus x squared over 4 alpha t. Okay, so then u of xt is going to be the convolution of g, which is just, it's given. That's something that's initial. We don't have anything. We don't have a formula for it. It's given, and the convolution with this right here. With the convolution, sorry, u of xt is going to be equal. Let me just write it. Oops. So it's going to be g of y, and then convolving with f. Well, again, this is f hat, and so it means that this right there is equal to f. Okay, now as far as y's and x's and c's are concerned, 1 over the square root of 4 pi alpha t is a constant, so I can just pull that out. So actually, let me be slightly more explicit about what's going on here. Whoops. So this is the integral minus infinity to positive infinity g of y f of x minus y dy. Okay, f of y is 1 over the square root of pi 4 alpha t, and then we have the integral minus infinity to positive infinity g of y, and then e to the minus x minus y squared over 4 alpha t dy. Okay, and there you have it. That's the solution. That is the solution to the diffusion equation if we're given initial conditions u of x0 is equal to g of x. Okay, so this thing here, that times that has a special name. It's called the fundamental solution. So the fundamental solution is equal to 1 over the square root of 4 pi alpha t e to the minus x squared over 4 alpha t. Okay, that's the fundamental solution. It's called the fundamental solution because it basically, well, it satisfies the diffusion equation, which we'll talk about in just a minute, and you can kind of get all of the other solutions from it. Okay, in this sense here, this is the formula. Okay, so let's compute what its integral is equal to. So we're going to have the integral from minus infinity to positive infinity, 1 over the square root of 4 pi alpha t times e to the minus x squared over 4 alpha t dx. Okay, I'm going to make a change of variables and say z is equal to x over the square root of 4 alpha t. Then dz is just equal to dx. Whoops, dz is equal to dx over the square root of 4 alpha t. And when I make my changes in my integral over here, what's going to happen is everything is going to get canceled except for the 1 over the square root of pi. And so this is going to be 1 over the square root of pi times the integral minus infinity to positive infinity. This will be e to the minus z squared. And again, when I change the differentials, that's canceling with that term there. dz. Okay, so this is just the integral of a Gaussian, and you can figure out for yourself why it's 1 by looking, the polar integration thing. However you want to do it, the integral is equal to 1. But even if you don't buy that, or even if you don't feel like thinking about that, it's clear that this is not a function of alpha or t. So this does not depend on alpha or t. And this is important theoretically later in the chapter. I don't know how much we'll talk about them in the lectures to show that various things converge to what they need to converge to. And also, it's also going to be helpful when we want to think, when we want to give this a probabilistic interpretation. So what this is saying is the solution is equal to 1 over the square root of 4 pi alpha t integral minus infinity to positive infinity, g of y e to the minus x minus y squared over 4 alpha t dy. Now, the phi, like the thing that we're integrating against, the phi of x minus y t, this is a PDF for normal distribution. I don't know exactly how to write this. It's the PDF for so phi. I'll just write it. I don't know why I'm not. Anyways, p is a probability distribution function for a normal random variable that has mean equal to x and has sigma squared equal to 4 alpha t. Okay, so then we can recognize this up here as being the expected value of g. Okay, so it's kind of like saying that it's saying it's the average value of g. So it's if you look at this, if you fix an x and t, the solution there is going to be equal to the average value of g, or the expected value of g, the expected value of the initial data. And you can read the sections in the book that make this connection to probability even more explicit and explain it even more than what we're doing here. It's not a coincidence that these things are sort of deeply linked. So what PDE does phi satisfy? Well, I'm gonna let you do this on your own. I want you to show that phi satisfies the t derivative is equal to alpha. Okay, so in other words, it satisfies the diffusion equation. Okay, but what are the boundary values? Like, what are the initial conditions that it satisfies? In other words, what about this? Like the solution, like the u of xt, u of x0, we think should satisfy u of x0 is equal to g of x. That's kind of how we derived it. Okay, but what about this? What are the corresponding boundary values for this? Well, if you look at the graph, so this is something that's proven in section 7 or in theorem 7.1. I'll talk a little bit about it in just a moment. But if you look at the graph, for very big values of t, it's going to be a bump like this, and then for very small values of t, as t goes to 0, it's going to be like this, and it's going to get peakier and peakier like this. Okay, and so what's happening, like pictorially, it looks kind of like it's converging to this Dirac delta function. If we think about the Dirac delta function as being something that's equal to 0 everywhere else, and infinity is 0. Of course, again, strictly speaking, that doesn't make sense. And strictly speaking, the fundamental solution is not defined when t is equal to 0. But what about the limits? We might be able to take the limits, and what we will show in a moment is that the limit as t goes to 0 from the positive side, so for any smooth function, phi of x this limit is equal to phi of 0. Okay, so in other words, this, as t goes to 0, this converges to phi of x times the delta function, or the delta not a function, dx. Okay, now I have to have the limit on the outside of the integral. This makes no sense if you put the limit on the inside of the integral. If you put the limit on the inside of integral, it's just going to be equal to 0 for all values, or it's just going to be equal to 0. Okay, so the only way this makes sense is if you have the limit on the outside of the integral. Here's a case again where you cannot change the order of the limit and the integral. Okay, so because we say that phi is converging, phi of xt is converging in this way, because the fundamental solution kind of converges the delta function in this way. Like you can't put the limit on the inside of the integral, it's only if you have the limit on the outside of the integral. Because it converges in this way, we say that this converges to delta as t goes to 0, and remember we say this is in the sense of distributions. Okay, and all in the sense of distributions means is that these integrals converge for every smooth function. it's weaker than saying that there's this pointwise convergence like functions, because again, we're not allowed to pass the limit inside there, otherwise this statement is not true. So we say in the sense of distributions, if it's true, if you have the limit on the outside of the integral, even if it's not necessarily true if you have the limit on the inside of the integral. Okay. All right, so what are some properties of the solution given, what are some properties of the fundamentals, what are some of the properties of the solution that we just looked at? So it says, prove that this formula satisfies the diffusion equation IVP, initial value problem. So I'm going to not talk about this one right now. You can look more about that later. Okay, so one is to show it satisfies the PDE. Okay, and to do that, you're going to differentiate under the integral sign and use this fact right there. So I'm going to leave that to you. So now I kind of want to show that the limit, now what I want to show is that so if you think about what's happening here, I want to show what we're asking. We've shown that U satisfies the PDE, or at least U will do that. I want to show that the U defined by the formula, I want to show that the U defined by this, where is it? I want to show that the U defined by this formula, I want to show that that U also satisfies U of x0 is equal to G of x. So in other words, what I want to show is that the limit as t goes to 0 of U of xt is equal to G of x for all x. Okay, and then U of xt when t is greater than 0, so U of xt when t is greater than 0 is going to be defined by the integral. So the solution then, when U of xt, when t is greater than 0, is going to be defined by the integral. And then when t is equal to 0, it's going to be G of x. Okay, and what we're saying is that this satisfies the IVP. It satisfies the initial value problem and is continuous. See, if we didn't care about a continuous solution, I could just say the solution is going to be equal to G of x when x is equal to 0, and it's going to be equal to 17. Sorry, it's going to be G of x when t is equal to 0, and it's going to be 17 when t is greater than 0. Okay, that's going to be a discontinuous function that satisfies the PDE. It satisfies the initial values, but the two pieces aren't connected and it's not continuous. Okay, so when we say that we have a function that satisfies the diffusion equation, what we really mean is the following. So let's think about like in the xt plane. This is x, this is t. We start with initial data here, G of x on the line. And then we form the solution U of xt that gives us a function up here. And we know this function up here when t is greater than 0. That's what you're doing in part 1 here. You're showing that that satisfies the PDE. And now what we're doing, we're saying if we take that formula and we take the limits back down, those limits are going to converge back down to G of x. Okay, and that's really what the solution, that's really what we should be talking about when we're talking about a solution to the diffusion equation. It should solve the PDE and its limits as you go down to the t equals 0 axis, to the x-axis, should converge back down to the initial values. Okay, again, otherwise you could come up with a ridiculous solution. If you don't have that like as something that you want, or if you don't want to use a solution to satisfy that, then you come up with ridiculous things. Okay, so let me talk a little bit about why this is true. So what we want to show is that, is that if I look at the integral minus infinity to positive infinity, so I'm just gonna, let me back up and okay, so the pen stopped working, so that's great. Okay, so what I want to show then, so I kind of want to show this. So this limit thing is supposed to be for all x, but I just want to fix x at equal to 0 and show the following. I want to show that the limit, or not even show, I want to talk about this. So the limit as t goes to 0, u of 0t is equal to g of 0. And then you can sort of see about how this would work for other values of x other than 0. Okay, so what this is equivalent to saying is that I can make is that there exists. So this limit means there is a delta greater than 0. Whoops. Man, I am like really having a hard time now. This means that for all epsilon greater than 0, there is delta greater than 0 such that if t is less than delta, then the following is true. The absolute value of the absolute value of g of y phi of x minus y, t dy minus g of 0, that this is going to be less than epsilon. Okay, so as long as t is sufficiently small, this is going to be less than epsilon. Okay, but now what we're going to do to show this, we're going to use the fact that the integral of that is equal to 1. So now we're going to do this cool trick. This is going to be phi of x minus y t times, whoops, that's supposed to be a parentheses, times g of y minus g of 0 dy. And I can do this because g of 0 is a constant and the integral of this is equal to 1. Okay, so I can combine this into the integral here. And if you're confused about why that is, just actually distribute the phi to both of these and compute each integral, and you'll see what I'm talking about. Okay, so I have this, but this I can move the absolute values inside. It's going to be less than or equal to the integral. Okay, now phi is positive, so I don't need to put the absolute values around there. And of course, x is equal to 0. So I'm just going to write this as minus y. But remember, it's actually an even function, so I can just write this as phi of y times the absolute value g of y minus g of 0. Okay, you can t. Man, sorry. Okay, if you have an integral with the absolute values on the outside, that's always less than or equal to if you put the absolute values on the inside. Because just draw a graph where you have a function that's positive and negative. There could be cancellation if you have the absolute values on the inside, but there can be no cancellation with the absolute values on the inside. Okay, and this is the integral. Let me write explicitly minus infinity to positive infinity. Okay, so choose a delta, I'm going to call it delta 1, such that the absolute value of g of y minus g of 0 is less than epsilon over 2 if y minus 0, so just the absolute value of y, is less than delta 1. Okay, and we can do this if g is continuous. So let's assume that g is continuous. Okay, if g is not continuous, we can make this work as well, but it's not as easy here. Okay, so now choose delta 2 such that if t is less than delta 2, then the integral, I'm just going to integrate over the values where y, we're going to integrate over the values of y where y is bigger than delta 2, bigger than delta 1, phi of y t dy is less than epsilon over 2. Okay, now why can I do that? What region are we integrating over? Well, remember, as t goes to 0, the tails of phi go down very quickly. Okay, and so if I'm just integrating from minus infinity to minus delta, and then from delta to infinity, I can always make t go down. I can always make t small enough, take t small enough, so that this inequality is true. Okay, and finally, combine these. Finally, combine and conclude what we want. Okay, now I know I'm being very purposefully vague here. I'm just sort of giving you the recipe on how to prove this rather than the proof. And the actual proof is in the book. But here's a recipe if you want to sort of think about it a little bit on your own before you look at the book. Do something like this first. And of course, we can talk about it in office hours, discussion forums, so on and so forth. I think that's all I'm going to say here because I want to get back to using the pin. So yeah, actually, I just want to say this. So I'm going to finish this. So what is the domain of influence? So with the wave equation, remember what happened with the wave equation. A disturbance took time to travel down the string. Okay, so if I had an initial distribution, like if I plug the string, let's see, if I plug the string here, it's going to take a while down the string for the string to even know it got plugged because that disturbance had to travel down. Okay, this is not the same with the heat equation, the diffusion equation. If I start on some infinitely long thing here, and I've got a function like this is going to be equal to 1, let's say, from minus a to a. Okay, we already looked at this. We already looked at functions like this and found the Fourier transform of it. But if you look at, if this is going to be if this is the initial data, like if this is our f of x, and we have our diffusion equation, the t derivative is equal to alpha times the double x u derivative and u of x0 is equal to this f of x. Okay, then just look at the formula. Then u of xt is going to be equal to 0, is going to be greater than 0 for all x if t is greater than 0. So this initial compactly supported data somehow will expand and propagate infinitely fast out to the farthest reaches of the x-axis here. Okay, so we call this infinite propagation speed because you have a compact thing that spreads out infinitely fast. Okay, so this equation has something called infinite propagation speed, whereas the wave equation has something called finite propagation speed. This actually makes a pretty big difference in the analysis of what's going to go on. This makes maybe it's not so much in this class though, a little bit. Anyways, it has infinite propagation speed. The other thing, I didn't talk about it up here, so the one that I scratched out, even for initial data that is not smooth, like the Dirac delta function, even if you look at initial data like that, the solution is still going to be infinitely smooth, which again is different from the wave equation, which if you had started with discontinuous data, you have a solution that's discontinuous. This is different. If you start with this continuous data, you get infinitely smooth data. Even if you start with a Dirac delta function, you get infinitely smooth. You get an infinitely smooth solution. Okay, and again, I'm gonna want this to be an exercise. You guys can do that on your own. Exercise, I don't know if I'll assign it, but you can do that on your own, and you can do this on your own as well. And by on your own, as always, I mean we can talk about it in office hours or the discussion forums. Also, these are like really good things. These are really good questions to have on tests and stuff like that. Okay, in the next video, we will look at this problem.